Hey everyone. So today what we're going to be doing is learning how to use R to create a general linear model that will give us bivariate estimates. So that means just looking at the relationship between two variables. And those variables could be numeric and numeric variables. And we would usually call that a regression. And we're going to be looking at a numeric and a categorical variable. And when we're doing that, normally we might think about that as a t-test. But I'm going to show you how to do that in R as a simple general linear model in both situations. So let's get right into it. Okay, so I've put myself down here in the corner, but it might actually be better for myself to be up a little bit higher. So that way we can see some of the figures that I'm going to be creating down in this bottom corner panel. What you can see is that I've already loaded up a script file, so that's going to make it easier for us to follow along, I think. So on the top line, what I've got is this command that says options scipen equals 999. Now, what that's going to do is it's going to stop R from outputting all of its values in scientific notation. And it'll give us actual human readable numbers. Now, you can turn that back by changing it to scipen equals 1, but I'm going to run that command by using Control Enter. You can also use the run command to run that once you've got it typed out. The other thing we're going to do is load up two libraries. The first one being FlexPlot. And if you haven't got that installed, you can't do it simply through the normal method. Look back at one of the other videos, probably the visualizations, the first visualizations video to find out how to do that. We're going to run that, load that library. We can see that's run. And then ggplot2 is another one that we're going to be using. So I've run that and it seems to be all good. So the first thing we're going to do is look at an example of a general linear model that basically looks at the relationship between two numeric variables. And in this case, it's the amount of weight lost as a function of your motivation. And we're going to take this from the exercise data, exercise_data dataset, which is actually included in the FlexPlot package. So once we've got FlexPlot loaded up, we automatically have access to this exercise data dataset. So typically what we want to do is just first look at the univariate distributions of the data to see that we've got, nothing funky going on. So if I just do FlexPlot weight.loss as a function of 1, that will do a histogram of weight loss, basically in the counts that we've got in the various bins from this exercise data dataset. So weight.loss as a function of 1, data equals exercise_data. Now, if I run that command, what we see is in the panel below me here, it's created a histogram. And we see that weight loss goes basically from -10, which basically means they gained 10 pounds or kilos or whatever it is, up to about 20. And the data looks reasonably normally distributed. I don't see any massive problems, but there's, the data falls within a range that we would expect. If we saw a -100 or a +1000, we might want to consider that we might have some issues with this data. So the next thing we'll do is look at the univariate plot for motivation in the same way. So you could just copy and paste that line, change weight loss to motivation. So motivation is a function of 1, and we run that command. And again, that creates this plot that we've got in the bottom corner, and it looks reasonably normally distributed within the range that we sort of expect. So the next thing we're going to do is look at the relationship between weight loss and motivation in graphical format to see if there's any issues that we can see in the data. And we'll use the FlexPlot function again and say weight.loss as a function of motivation. So what this will do is put weight loss on the vertical y-axis and motivation on the x-axis. And again, data equals exercise data. Now, if I run that command, what we see is the figure gets plotted below us, where we've got a scatter plot of all of our data points, where any value of weight loss is associated with its value of motivation. And it's plotted a lowest line through the middle, which is basically, you can think of like a running average of sort of like the most dense part of the data. Now, we use a lowest line here because we just want to see if there's any major curve in the data. And it looks like there might be a little at the beginning and the end, but sometimes that's just a function of there being fewer data points at the beginning and end. So instead, we're going to make FlexPlot here use a linear model, just a straight line, because that's what we're going to be calculating with our GLM, is basically the straight line that runs right through that data. So we'll do the exact same command, but this time we're going to add onto the end of it, method equals LM. When we run that, we get a nice straight line through our data, and it looks like it is following the data quite well and looks pretty good. Okay, so now that we've looked at our data, let's get on to actually figuring out what the actual estimates are, or what the values for this line are, because that's what we want to know. What is the intercept and what is this slope? What's the value of this slope? So the way we do that is by using the LM function. And LM simply means linear model. And you'll notice its structure is exactly the same as the structure that we have up here for FlexPlot. We just don't need this method equals LM part because it's a linear model already. So if we do that, we say weight.loss is a function of motivation, comma, data equals exercise data. We'll look in the bottom panel here in the output panel at what it gives us for that. So if I hit Control Enter, it says, okay, it's given me back what my command was, and it's giving me my coefficients. And that involves the intercept and the slope here. So the intercept is negative 3.3377. And the way we would interpret that is that if motivation is at 0, our weight loss would actually be negative 3.34. So basically, we would gain 3 pounds or 3.5 pounds if our motivation was 0. Now, this value here, motivation, is the slope for motivation. So each time the value of motivation goes up by 1, we have an increase in weight loss of 0.1856. Now in the figure over here, we can see that actually our value here doesn't go all the way to 0. So we can't see that the intercept is negative 3. So what I've done here is I've created another FlexPlot graph that uses the same structure as we had before with the LM, but I've added 2 extra things. I've put them on 2 lines so we could see them all here. The first thing that I've added is plus xlim bracket 0,90. And what that will do is make the x-axis go from 0 all the way up to 90. And then this extra part here, plus geom underscore smooth, method equals LM, full range equals T, basically makes it so the line is extended all the way for my entire range. So if I run that command, you'll get to see that. We've got that same data plotted, but what we can see here is that now my line, or my regression line, goes all the way to the intercept, and that matches up very nicely with our intercept here that says it's negative 3.33. That looks about right. Okay, so we've gotten our intercept and our slope by just running this command LM. But often it's a lot nicer just to save that linear model into an object. So the way we do that is just by doing the same command here. We take that LM, and what we're going to do is use our assignment operator to put that into some sort of object. We call it whatever we want. I'll just call it model for now. So into model, we're going to put the LM that we just made. So I run that, and what we see is right behind me here, we get a new object here called model of type LM, and it's got a bunch of things in it, list of 12. Now, if I just call that object again, and I just run model, we'll see that it gave me the same thing as just running this command on its own. But there's a lot more pieces of information inside that model besides just the intercept and the slope. So I can access that by using the function summary. So I want a summary of model. And if I run that command, what we see is we get a lot of information in here in our output panel. So the first thing we see is the residuals. And the residuals just tell us basically how far away these dots are from our regression line. So the minimum is 13 under, the maximum is 10 under, and then basically gives us the median and the quartiles of how far away those residuals are. It also provides us with those same coefficients that we saw, this slope and the intercept here, where we have the intercept being negative 3.33 and the slope being 0.185. It also gives us standard errors of the intercept and the slope, and it also gives us t-value as well as the probability. And now what this probability is saying is the intercept significantly different than 0? And of course, it's negative 3.33. We know it's different than 0, but because there's a standard error associated with that, we're actually not sure 100% that in every sample it would be less than 0. So that's why the p is greater than 0.05. And motivation, we have a t ratio and a p-value that is quite small, a bunch of zeros followed by a 271. So that is certainly less than 0.05. And it just simply tells us that with this data set, the probability that we would see a slope this big if there is actually no slope in the data, in fact, that you just draw a flat line through the middle, it just says that it's much more likely that this fits better. Now at the bottom, it also gives us our R squared value, both multiple R squared and adjusted R squared, and then an F statistic, but don't worry about that now because it's not really super useful until we get to multiple predictors. All right, so there's another way we can extract some of these values, and it's another function that's actually built into the FlexPlot package, and it's called estimates. So we can instead use estimates brackets model to get some of the same values out if we want instead. So if I run that command, here the first thing we get is our R squared, which is 0.125, which basically says that this model explains 12.5% of the variance as compared to just a mean going through the middle with confidence intervals ranging from 4% to 21%. It also gives us our correlation coefficient, which is just actually R squared, the square root of that. So we can calculate that if we like. And then it gives us similar things for our intercept and our slope. We get similar values, but we also have confidence intervals for the intercept and the slope from this function. Now, if we wanted to just not use the estimates function and we used the summary, we wouldn't have gotten a correlation coefficient. So if we wanted to not use the estimates function, we can use core.test, and then we need to basically give it this command here to get the correlation coefficient for the data. So we need to specify the data set, exercise underscore data, and then which column, weight.loss, and then exercise underscore data, motivation. So this just does a correlation test between these two variables. And if I run that command, what we see is we get a Pearson's product moment correlation coefficient, and we see that it's 0.353. And that's essentially exactly the same value as we saw by running this estimates function. The other thing we see is that we get a p-value for that that is 0.00002714. Now, notable is that that is exactly the same p-value we get for the significance value of the slope. So what that tells us is that in a linear model that's only got one predictor, the correlation coefficient and the slope of the model are going to be basically the same thing. One is just a standardized version of the other one. Okay, so let's go through a second example of the same thing. So we're going to look at speed as a function of IQ from the Avengers dataset, which is a dataset that is included in FlexPlot as well. Now, like I said earlier, it's a good idea to go through and look at the univariate distributions to see if you've got any problems with the data. So we'll do that first by looking at this function or using this command that says FlexPlot speed as a function of 1, data equals Avengers. And we get a graph below us where we have most of the data looks like pretty normally distributed. Looks like we might have one outlier. We're not going to worry about that too much right now because there's a lot of data in this data set, and this outlier is probably not going to have very much effect. The other one we'll look at is IQ as a function of 1. So we'll get a histogram of IQ values. And again, it looks like everything looks like it's in the range that we would expect from about, just under 90 to almost 140. So those values look good. So we'll then do a bivariate plot of speed as a function of IQ with data equals Avengers and method equals LM. Now, as you would expect, you probably don't think there would be any kind of strong relationship between speed and IQ. Why would IQ have any effect on your speed? And that's really what it looks like from our graph. But we can then get these values and we can start to see if there is any effect at all. So we're going to create a new model by basically taking an LM of speed as a function of IQ, data equals Avengers, and we're going to drop that, or we're going to use our assignment operator to put that into an object called model2. So if I run that, we get a new model object called model2 up here in my environment. Now, again, I can ask for a summary of that. And what we see is, first of all, we've got our residuals, but what we want to know is our intercept. So our intercept basically says, well, what is our value of speed when IQ equals 0? So in this case, the intercept doesn't really make a lot of sense because we would have no cases where IQ would equal 0. So what we know, though, is that we need that value in order to be able to calculate any other value. So we need that value, and that's okay. And the question is that significantly different than 0? Yeah, but we don't care. So that's a value you can completely ignore. Now, the question we have is there any relationship between IQ and speed? And it looks like that for every increase in IQ score by 1, we've got a corresponding decrease in speed of 0.0014. So it's really, really small. It's a small value. And that is just not quite significant. And the only reason it's actually even close is because there are so many data points. So it's this really small effect. And in fact, you can see that that effect is really small because if you look at the R squared value, we see that this model is only explaining 0.45% of the variance in the data. So a very, very small amount can be explained. So it's a really, really small effect. And we see that again, if I run estimates of model 2, we'll also see that the correlation coefficient is 0.07. So a very small effect. If we're going to think about our general interpretations of what effect size means. Okay, so That's basically it, and this is what we would typically call a regression analysis. But it's also really easy just to think of it in terms of a bivariate numeric general linear model. So now we'll look at the relationship between a numeric variable and a categorical variable. And previously we might have thought of this in terms of using a t-test to look for differences between groups or something. So in this case, what if we wanted to look at weight loss as a function of gender? So does gender being male or female, did that result in a larger amount of weight loss from this exercise data set? Now remember, we typically want to look at the univariate distributions. We've already done that for weight loss once previously, and remember we see that this nice histogram, it's a little bit skewed. Also, if we want to look at our univariate distribution of gender, that will give us basically the count of number of individuals that we have in each of those two categories. And what we see is we've got, looks like almost twice as many females as there are males in this data set. So that might be something to think about, but it probably doesn't matter too much for analysis here. So then we're going to look at the bivariate plot. And what this is going to do is plot weight loss as a function of gender. So if we run this command, what we see is we get this, what we call a median dot plot. So the dot in the middle is the median. The whiskers, or the two lines, the upper and lower lines, give us the boundaries of the lower and upper quartiles of the data. And then we've got all of the data sort of presented over top of our median. And we can see that there's, maybe a little bit of skew, but it's not too bad. So the next step would be to create a linear model of this. And we can think about this the exact same way. So just imagine that all of these dots are actually lined up along female here, and all of these dots are lined up along male. And now we're going to do weight loss as a function of gender and put that into an object we're going to call model T. The reason I called it model T is because typically this might be known as a t-test between two independent groups. So if I create that model, you can see it's joined our global environment up here. I've got model T. And if I just call that object, we see we get the same coefficients. We get an intercept and a slope. Now, what's the intercept? Well, the intercept is simply the mean of one of the groups. And how do you know which one? Well, it actually tells you what the slope or the difference is for the other group. So we know that because gender female is for the slope, we know that the intercept is pertaining to the males here. So the mean of this group here is going to be 6.0588. And the difference between these two is 0.759. So females are actually had 0.759 pounds more weight loss. Okay, so if we do a summary of that, we'll see the same thing. So we see that our intercept is 6.0588. So that's the mean weight loss here for males. And females have an increase of 0.7594. Now, the intercept is saying is weight loss greater than 0 for the males. And in this case, yes, that is significantly different than 0. And the slope here is asking, is the slope between male and female greater than 0? Or the other way we can think about that is the difference between these two groups different than 0? And the p-value is 0.369, which says, no, it's not significantly different than 0. This model also gives us an R-squared that basically says this is explaining 0.4% of the variance, but it's not as useful when we're thinking about this in terms of categories. So we can also do an estimates function of model T. And when we do that, we see, okay, we get a model R-squared, which says the same thing. It explains 0.4% of the variance. And it also will give us estimates for each of the two categories. So we see gender male, we have an estimate of 6.06 as the mean, and female, the weight loss is 6.82. And if you take the difference between those, we see the male versus female difference of 0.76. We get upper and lower confidence intervals and a Cohen's d of 0.13. So this basically says that the mean difference, when expressed in terms of the number of standard deviations in the data, is 0.13 standard deviation. So it's actually quite a small effect. So I told you that this linear model is basically the same thing as doing a t-test. And I can show that to you by actually creating a t-test. So if instead we did t.test, weight loss as a function of gender, data equals exercise data, then we have to also make this assumption of equal variances being true and put that into an object that we call t. If I run that command and then just call t, what we see is we get a t value of 0.899, negative 0.899, and a p-value of 0.369. Now, if we go back up to our model, we see we get a t-value of 0.9, which is basically the same as 0.8997 rounded up, and a p-value of 0.369. And we see the p-value is 0.369. So we're getting the exact same values out of our linear model as we are getting out of our t. Now, also, if we, instead of doing estimates, we wanted to calculate Cohen's d directly, we could do that in a couple of different ways. We could use the library effect size. So you load up the library, open bracket, effect size, and run that. We're going to need that in order to use this function, Cohen's underscore d, open bracket, weight loss as a function of gender, comma, data equals exercise data. So what this does is basically says, hey, look, do a Cohen's d of this model that we just did previously. And when we do that, it gives us a Cohen's d of 0.13, which is what we saw before, as well as 95% confidence intervals of that Cohen's d. We can do the same thing from a library called psych. So library psych, if I load that, remember, you may want to install this package if you don't already have it installed. And from this, we're going to use the function Cohen.d and then the same structure here. If I run that, we get essentially the same thing. We get a weight loss. We've got an effect of 0.13, lower and upper confidence intervals for that. We can also calculate a Cohen's d using this function t_2_d. And we take it from the model that we created that was called t, and we have to ask it for the t ratio. So t $statistic will actually put out the t ratio, and then t $parameter will give us the degrees of freedom. So our t ratio to d will allow us to calculate d from the t ratio and the degrees of freedom. If I run that, we see we actually get the exact same thing, 0.13, and it's got our confidence intervals that are slightly different. We could also calculate R in the same way. So T to R would give us from the T statistic and the T parameter. This will give us our correlation coefficient, which is not really as easy to understand with a categorical variable, but we can get it, and it's negative 0.06, which we understand is actually quite a low effect size. So let's do one more example. This is a categorical and numeric example again. So we'll use the shoes and flip-flops data. So the data set is shoes_flipflops.csv and should be linked. So we're going to read that into an object called shoes_flipflops. Now, what this data set does is it's got average 10K running time for people who ran a 10K in flip-flops versus shoes. And there's other pieces of data in there, like the number of blisters that they sustained and things like that. So what we want to do is first, we want to determine whether or not our data looks reasonably good, whether the values are what we would expect. So if we look at the data set, we'd see that some of the variables are finish_time, both with capitals, and footwear. So we're interested in looking at finish time as a function of footwear, but we want to look at those univariate variables first. We've got an extra space in here. I'm just going to get rid of that in multiple places, in fact. Let's do that. Okay, so if we do finish time as a function of 1, that should give us a histogram of different finish times. And we see that looks like there's actually, this is bivariate or bimodal data. And maybe that's not too surprising considering we've got two very different groups in this data set. We can also look at the size of our groups, right? Do we have some kind of weird missing group? Do we have a third group? So we'll look at footwear as a function of 1, just to give us an idea. It looks like, no, in fact, looks like we've got exactly 10 people in each of these two groups. Great, looks good. So then we'll do the bivariate graph, which shows us finish time as a function of footwear, and data equals shoes _ flip-flops. If I run that command, what we see is we get our median dot plot down below me here, where we have our flip-flops group has a finish time of, looks like on average, somewhere around 200 minutes. And our running shoe group has a finish time somewhere around 50 minutes. Okay, so again, we can use our linear model to create a model of that, or our LM function to create a model of that using the same structure that we use for FlexPlot as well. And we'll put that into some object. Here, I'm going to call it SFF, so shoes, flip-flops. If I run that command, I should get an object in behind me here called SFF, and that's a linear model. And I can do a summary of that. If we look at the summary, we see that our intercept is 189.420. Now, just looking at that, it seems like that must be the flip-flop group. But we can also look at our slope for footwear and see that, oh, the slope for shoe basically says that it decreases by 137 minutes. Now, of course, our intercept is asking, is our estimate of 10K time significantly different than 0? We go, yes, of course it is, so I don't think we care about that. Whereas the slope says, is there a difference between our two groups? Is the slope between the two means, and that is the difference between the two means, different than 0? And of course it says, yeah, it's negative 137 minutes, and it's got a p-value with a lot of zeros in front of it. We can also see that our r² value is 0.962, suggesting that a lot of the variance is explained by group. If we then use the estimates function, we can see that the r² value is given to us, and as well as the estimates for the factors. So we get our estimate of the actual finish time, which is 189.42, which in fact was the intercept, but it also gives us the finish time for shoes, which is 51 minutes. So that's just simply calculated from taking the 189.42 and subtracting the difference, minus 137.73. We know that the running shoe finish time was on average 51.69 minutes, and it gives us our upper and lower confidence intervals for both of those values. It also gives us our difference and upper and lower confidence intervals of those differences, as well as a Cohen's d value of 9.55. We can also get those values by actually using the describe by function that we saw a couple of videos ago from the package psych. And again, remember, look at this, the structure is exactly the same. If I run that, we can see we get means and standard deviations for all the data, but we can get our mean finish times for each of these groups, as well as range, etc., etc. We can also calculate Cohen's d like the way we saw before. Cohen's underscore D, finish time as a function of footwear, data equals shoes, flip-flops, and paired equals false in this case. And that gives us a Cohen's D 9.55, which is basically the same as what we got in our estimates function up here. All right, so hopefully that's given you a little bit of practice on being able to use linear models in R with bivariate data. So for doing numeric on numeric, which we basically would have typically called a simple regression, or using numeric data with categories, which we would have previously used or called a t-test. But again, you can do both of these using the simple linear model function. All right, I'll see you next time.